just want to drill down into some of the detail of the thermal issues and the difference between the GaN that's available now, SiC that is starting to gain popularity, and our solution, and why it's important. So we spoke before a little bit about the fact that we have a different thermal solution and we have much lower wastage of power, and that's really significant, and these graphs talk us through that. So this first graph, what we've done is we've taken basically an integrated GaN solution, one of the premier ones available today. And one of the things that they can do is they can slow down the switching transition. So they can make it like a SiC or a silicon transistor in terms of the switching speed. And the idea behind that is that you can mitigate your EMC problems and thereby have a simpler design solution. The problem with that is, if you look at this graph, so this is for a specific, I think it's a 5 kilowatt converter, and we've worked out all of the power dissipation that you would get with a SiC solution, which is this blue trace at the top here. And then we've made the integrated GaN solution switch at the same speed as SiC, so it will make it look like it's a SiC transistor, so that you have the same EMC performance. And that's what you get here. So you get almost the same level of loss. There's a slight difference because SiC, it has the parasitic diode, so you'll get a switching loss on every converter switching cycle, whereas GaN, it doesn't have that. So they're switching at the same speed, but you've still got a small difference because of the difference of the physics of the transistors. But what you really see here is the third trace, which is our solution, which is our QGaN solution. Now this has totally different performance characteristics. Firstly, it's switching in 2 nanoseconds or less. So the amount of power that we're dissipating or losing every time we switch is very, very small. So we're not actually throwing much power away. Secondly, we've got incredibly low thermal resistance. So normal packaged GaNs, as we spoke before, they're very small devices, very difficult to get the heat out of them. But with our solution, basically the heat just comes straight out. We've got the lowest thermal resistance of any component on the market. So we're basically flatlined. So as the switching frequency of the converter goes up, our power dissipation doesn't really go up very much. It's almost flatlined. So that means that our losses don't go up. What does that mean thermally? So look down here. So essentially we've got the same 3 graphs. Now, this is now showing temperature of the junction. So you have a maximum junction temperature. So for GaN, it's 150 degrees C, and for SiC, it's about 170. So you can run them a bit hotter. But because you're dissipating more energy, you're throwing away more power, you've got to get rid of it. And because all of the solutions out there are not well packaged in terms of thermal performance, that energy is trapped inside. So the junction temperature goes up much more rapidly. So as you increase the frequency here, you can see the junction temperature goes up really rapidly. So at this point here for SiC, this is about 650 kilohertz, you get to the maximum junction temperature. At that point, you don't have a working converter. It's got zero capacity for switching power. So you're actually really only able to work sort of down here at a few hundred kilohertz, really absolute maximum. Whereas the controlled edge speed GaN solution, it's got slightly lower losses because it doesn't have the diode. So it can get up to about 1 megahertz before it hits its junction temperature. But remember, that's the point at which it's at maximum temperature. It can't operate as a switch anymore. So it can really only work at maybe 500 kilohertz in reality. But the integrated drive GaN transistors can actually go faster. These are all if you normalize the speed of the GaN transistor to a SiC transistor. If you wind it up so it goes as fast as it possibly can, this is a slightly different scale. This is up to like 300 degrees up here. Obviously, it's not functional here. So this is a different scale. And this is the maximum junction temperature here for GaN. And it's sitting at 2 megahertz. So people are claiming 2 megahertz converters are possible with these GaN transistors. But in reality, that's at the maximum junction temperature. That can't switch anymore. It can't actually switch any power. So in reality, these can actually only work down here. And the reason why we're so much lower than that is that even at the fastest speed of integrated GaN transistors, we're still 3 or 4 times faster. So we've got 3 or 4 times lower power dissipation and, of course, much better thermals. So this really demonstrates that essentially the QPT GaN solution you can use it anywhere up to 2 megahertz without any problem whatsoever. You don't get the massive hit in performance that you get with other thermal and low switching speed designs. And lastly, what we're looking at here is we're asking the question, is GaN really a good replacement for SiC? So if we look at integrated GaN drives, integrated GaN-driven transistors, if you go really slowly, so you make it look like SiC or silicon, yes, you get away with the EMC problems. It's not a super complex design, but you're basically at the same level of efficiency. You haven't really gained anything, and you've had to redesign your product and not really gained anything. So then the next option is, okay, you make it run really fast. Yes, you can do that. You save a bit of power. So you might have a more efficient design. But then because of the switching speed of the edges, you've got horrendous EMC problems. So this is an incredibly complex redesign for a relatively small amount of advantage, because you can see here it's still dissipating much more than we are. And then there's the third option, which is to use our QPT Q-GaN module, which gives you the best of both worlds. It gives you amazing thermal performance, it gives you no EMC issues, and essentially you can run up to 2 megahertz without any problem at all.